Okay, guys, so today we're going to finish up chapter 2. This is chapter 2.4, graphs that enlighten and graphs that deceive. I think in your homework it might end up being called chapter 2.3. Remember, again, don't line up the notes perfectly with the homework. You just try to think of the concepts. It'll always be off by about one section because I'm using notes from an older edition of the book. Okay, so we're going to talk about a lot of graphs in this section. So in terms of quizzes and stuff, you're probably going to get like one of each type of these graphs on your quiz. You'll see some in the homework to practice. So here we have a frequency polygon, uses line segments connected to a point to points located directly above class midpoints values at the height representing the frequency for the class with that midpoint. So basically what we're going to need to do is we're going to need to find class midpoints for each one of these classes, just like we did in the previous problems. So if we look at this problem, we see that we could have a class midpoint of 89.5. What's the next one? 109.5. Geez, I'm not writing small enough. 89.5, 109.5, 129.5, 149.5, 169.5, and 189.5. Okay. So let's see here. So at 89.5, we have 9. So what I'm going to do is I'm going to make and label this. Let's do this as 89.5. Let's go 109.5. Let's go 129.5. Let's go 149.5. And I'm just going to continue this on. Okay. So 89, 109.5, 129.5, 149.5. We need another one, 169.5, and one more, 189.5. Okay. So let's go by tens. I guess we could go by 5. So 5, 10, 15. You know what? Let's go a little bit better than that. Let's go. Here's 10, here's 20, here's 30. So 10, 20, 30. And then if we want, we can do this as 5, 15, and 25. Okay, so for 89.5, we have 9. So that'll be right about, you know what, I'll do it in a different color. That'll be right about here, right? So that's about 9. Let's do 24 for 109.5. That'll be right about here, okay? And then 129.5 is going to be 5, so that'll be right about here. 149.5 is 1, so that's going to be really way down here. That's going to be right about there. And then 169.5 is going to be 0, so that'll be right there. And then 189.5 has 1 again, so that's going to be right there. Okay. Now I believe your book asks you to start at 0 right here, so they actually put a little point right there for 0. It depends on how they word the question, but I would put probably this extra one here to start at 0 because there obviously is nothing before 89.5. There is nothing in the 79.5 range. So we're going to start it at 0, and we're just going to draw line segments. We're not going to draw a smooth curve. This is called a frequency polygon, not a smooth curve. Okay. Oops. Okay, so these are straight lines, the best I can draw. Oh, geez, that's pretty bad. Okay, so these are supposed to be straight lines, little miniature line segments. So it says right here, line segments. So don't try to make a smooth curve. These are actually little line segments in between each midpoint. And you could do the same thing with a relative frequency polygon, but instead the relative frequencies would be, decimal points, like 0.10, 0.20, 0.30, so on and so on and so on. Okay, so that's a frequency polygon. I'm actually not going to go over in Ogive. It uses line segments connected to points, but the horizontal axis uses class boundaries. and the vertical axis uses cumulative frequencies. I guess we could do this one. I don't spend normally too much time on it, but I guess we could do the class boundaries. So here would be 79.5. The next one would be 99.5. The next one would be 119.5. Because remember, this is the same problem that we already did in terms of the blood pressure. Now it has the cumulative frequency added to this, but it's the same problem we've been working on in the previous section. So 119.5. What is this next one? 139.5, 159.5, and 179.5, and then 199.5. Okay, and then it uses cumulative frequency instead of regular frequency. And remember, cumulative just means you add up all of the values that are at your class interval and then what came before it. So I'll try red this time. Maybe I can use it with a smaller marker. Okay, so 79.5 had 0. Right, oops, let me do the heights. Let's do 10, 20, 30, 40, 50. No, we only need to go up to 40. So 10, 20, 30, 40. So this will be 10, 20, 30, 40, and then this will be 5. Okay, so let's do the red. So at 79.5, we have 0. At 99.5, we have 9. So that would be right about there. And then at 119.5, we should have 24. Oh no, I'm sorry, it's 9 plus 24, which would be 33. So then we're at 119.5, we go up to 33. Let me see, where's that gonna be at? Right about here. And then at 139.5, we're gonna go up to 38. Oops, that's almost a little too high. Let's go right about there. And then 159.5, we're gonna go to 39. And then 39 again for 179, and then 199, we're gonna go to 40. So it's gonna go like this, like this, like this, like this, like this, and then like this. Again, I don't use this one as often, but in case you see it in the homework or the quizzes, this is how you can do an OGIVE. Dot plot. Dot plot's a pretty straightforward one. It does exactly what it sounds. So what we're going to do is we're going to use this little, it says a dot plot shows dots for each observation placed above a horizontal scale of values. Dots representing equal values are sketched to construct. Draw a horizontal line, label the line with the name of the variable, and then label the line with values in each interval. You want to look at the minimum and the maximum observations. For each observation, place a dot above its value on the number line. So it looks like the biggest value is like 124 or something like that. And the smallest value is going to be what, 60? Yeah, so I'm going to start my labeling at 60. So let's put 60 here. Let's do 70. You know, I'm going to spread it out a little bit more. 70, 80, 90, 100, 110, 120, 130. So 70, 80, 90, 100, 110, 120, 130. And we shouldn't need any more than that. I think I spread it out too much in the beginning. Let's do this. Try to have it a little bit more equal. So 80, 90, 100, 110, 120, 130. Okay, so what you do is you take dots and you put them above the value. So let's see here. How many 60s are there? There's 1, I think there should be, here's 2 and here's 3. So I'm going to literally put 1 dot, 2 dots, 3 dots to symbolize that I found 3 60s. Okay. Then the next thing I'm going to do is find the next smallest number. Well, the next smallest number is what, 64 maybe? I think 64. So here's 1, here's 2, here's 3, here's 4. So 64 is going to be right about, so if this is, you know, 1, 2, 1, 2, 3, 4, so there'd be right about 64 right there. So I'm going to go 1, 2, 3, 4. So that's 64, right? Now, what's my next smallest number? I see 68. So let's see, 68, 68, 68. So we've used 60. Here's a 68. We've used 64. Here's a 68. We've used 64. We've used 64. We've used 60. We've used 60. We've used 64. So I see 1, 2, 3, 4, 5. So at 68, I'm going to do 5. So 68 would be right about here somewhere. 1, 2, 3, 4, 5. Okay, so we've used all these guys now. I'm just doing this to kind of keep track. The next number is going to be 72. So here's 1, 2, 3, 4, 5, 6, 7, 8 72s. So 72 is going to be right about here. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 72s, and you kind of try to space them evenly, just like you were doing the other numbers, to give a kind of a fair assessment. All right. And then 76 looks like the next one. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Yep, 6. So that would be right about here somewhere. 1, 2, 3, 4, 5, 6. All right, and what's our next number? 80, it looks like. So here's 180, here's 2 80s, here's 3 80s, here's 4, here's 5. So it looks like about 5. Maybe there's one more I missed. Oh, here's another one. Here's 6. So 1, 2, 3, 4, 5, 6. Okay, now let's go to 88. Here's 1, 2, 3, 4, 5. So 88 would be right about here. 1, 2, 3, 4, 5. And now what's the next one? It looks like what, 96? Here's 196, and that's all I see. So 96 would be right about here. I'll just put 1. Now what's the next one? 104 maybe. So 104 would be right here. I'll put 1. So here's the 104. So what do we got left standing still? It looks like just a 124, right? So then here's 124 over here, and we'll put 1 there. And I think that's everything. Yeah, I think that should be everything. So there is our dot plot. Now, as you can see, it's pretty nice. And if you wanted, you could kind of build something that looks like a histogram, right? You know how I shouldn't say a histogram, but remember how we drew the histogram and we followed the curve? All right. So we could build something like that. So a lot of these shapes could be used to kind of relate, oops, I erased one, to relate back to histograms and other graphs that we've been doing, and to talk about skewness and everything. Now, hopefully you guys are seeing that there is a slight flaw with this technique. Yes, it's good. Yes, it's obvious. I can obviously tell that this is where the most data was. It kind of looks like most of the data is centered around here. So we could do our counting and find the median or the center of the data and stuff like that. We could even do the average once we get, going with average in chapter 3. So I see all of that, but I do also notice something could be a little bit of a pain. Do you guys see, what if you had 10,000 pieces of data? Do you see this being a problem? Right. So this is a really good method that's cool and all, and it's very obvious and it's easy to do. But when it's large data values, you don't want to use a dot plot. You would rather use a histogram. A histogram would be much better for large data values. But in this case, with 40, it's manageable. It's something we can do, and it gets the point across, and we kind of see a skewness. We can find the center of the data, you know, things like that. So it's actually good for what it's for, but again, it's not really a comfortable way to work with large data sets. Okay, so let's move on to the next one. So stem plots, stem and leaf plot, represent quantitative data by separating each value into two parts, the stem and leaf. Stem plots are used to graph quantitative variables with small number of observations. So again, we don't want to use like a huge data set. We would probably use a, what's it called, a histogram for that. So to make a stem plot, put all your data in order from smallest to largest, separate each value into a stem and a leaf. The leaf will be a single rightmost digit of the number. The stem will consist of everything else to the left of the leaf. So the leaf is the rightmost number, so the stem will be the number, all the numbers to the left. In this case, all these numbers are two-digit numbers, so it kind of works out cleaner. So let's take a look at this. So what I'm going to do is, it looks like they're already arranged in order. So it says the Modern Language Association provides listening tests that measure understanding of spoken French. The range of scores is 0 to 46. Here are the scores of 21 high school French teachers at the beginning of an intensive summer course in French. And they're already done in order, so we don't have to rearrange them ourselves. So it looks like we're going to have stems of 0. We're going to have a stem of 1, of 2, of 3, and of 4. And then what we're going to do is we're going to put the leaves. So how many of these numbers have a 0 in the tens place? That would only be the number 9, right? Now, how many of these numbers have a 1 in the tens place? Well, that would be only the number 15, okay? How many of these numbers have a 2 in the tens place? Well, that would be the 20, the 20, the 22, the 23, the 23, the 24, the 24, the 25, and the 29. You see that? And that's all you do. So this is all, so this is the leaf, and this is the stem, okay? So then 30 has 30, 30, 31, 31, 32, okay? And then 40 has 40, 42, 42, 45, and 46, okay? Now, once again, if we wanted, what we could do is we could try to think about this. What if this were a histogram? Wouldn't I do something like this? And then, you know, I could rotate it and turn it 90 degrees. So then it would be like a normal histogram that we would be used to. So instead of being a up and down histogram, or what's it called, a stem plot, a stem and leaf plot, we could turn it into a histogram. So this is another way of thinking about it. And again, this is okay because it's a small number of values. If it was a large number of values, we would just go straight to the histogram. But again, we can kind of see how this could take on the shape of a histogram as well when it comes to skewness, okay? So if we wanted to, it says, determine the shape, center, and spread of the stem plot. So the shape, I would say, would be left skewed. Okay. Because if you were to draw, you know, like this, it looks like that it's skewed more on the left-hand side than the right. But again, that it's not overly done that way. The drawing doesn't do it justice. If we were doing something with the histogram, it would be a little bit more obvious. I'm kind of not drawing it perfectly. The center, so how many data values are there? So there are 21 data values. So we're going to do 21 plus 1 divided by 2. So that equals 22 divided by 2, which is 11. So what we need to find is we need to find the 11th data value. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so the number 29 is the center. Now you may be asking, well, why aren't you doing an interval? Well, because we're doing a stem and leaf plot, we have the actual data values, right? We don't have to guess at what the data values are. If we scroll back up here and we're looking at the center, they're asking for the median interval because all of this is put in intervals. We don't actually know the exact data values. We just know that this is the histogram for it. In this problem, over here, we know the exact data value. So we don't have to find an interval. We can find the exact data value that is the center. So in this case, 29 is the center and no interval needed because we actually know what is the center of the data. It's the number 29. It is the 11th data value, and we counted until we found the 11th data value, and it is 29. So the spread would be from 0.9 to 46, okay, points. Or you could even put just 9, okay, 9 to 46. But the reason I did 0.9 is because that's how we wrote it in the stem and leaf plot, okay? Let's go on to the next one. Split stem and leaf plot. We could do this. So the split stem and leaf plot, sometimes regular stem plots do not provide the picture detailed enough. In this case, we write each stem twice. The first stem is assigned to the low leaves and the second stem is assigned to the high leaves. So there's also back-to-back stem plots. This type of stem plot is used to compare two different data sets. The guidelines are the same as the regular stem plot, except the two data sets share the same internal stem. One set of leaves for one data set will extend to the left, and the other set of leaves for the second data set will extend to the right. For this one, we're just going to do the split stem plot. So it says in 1798, Henry Cavendish measured the density of Earth using an instrument called a torsion balance. While the density is obviously not uniform, the values of the mean density is important in determining the Earth's composition. The units are in grams cubed, or grams per centimeter cubed. Okay, so we're going to construct a split stem plot for this. So what I'm going to do is I'm going to use 4 and 4 twice, and I'm going to use the lower part of 4 and the higher part of 4. Then I'm going to use 5 twice, and then I'll use 6 twice if necessary, but it turns out there's not an extra term for the next 6. Okay, so for 4, we're going to do 4.1 and 4.3. For 4.9, that one goes here, right? Because these are the higher end of 4. For 5.3 and 5.3 and 5.3 and 5.3, how many are there? 1, 2, 3, 4, 5, 6. And then 5.4 and 5.4 and 5.4 and 5.4. Then for 5.5, we have 5. Let's see how many. 1, 2, 3, 4. And then how many 6s? 2, 4, 6. And then 5.7, 8, and 9, and then 6.4. So we don't need this other one. So once again, this would be a left skewed. And then the center would be 5.5 grams per centimeter cubed. And what we do is, how many data values were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24, 25, 26, 27, 28, 29. So we're going to do 29 plus 1 divided by 2, which is 15. So I'm going to count the 15th data value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's where I got the 5.5 from. Or you could do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so the 15th data value is the center, and as it turns out, that is the number 5.5. Our spread, once again, is 4.1 to 6.4 grams per centimeter cubed. And this is how you can do a split stem plot. Okay. Below is a regular stem plot of weights of college students, then the corresponding back-to-back where the original 50 weights are presented back-to-back by gender. So this is a stem and leaf plot with 50 values. And then what they did is they wanted to do the same, use the same data, but then separate the data by female and male. So this is what a split, what is it called? A back-to-back, I'm sorry. A back-to-back stem plot would look like, okay? So over here, they put all of the values that were female here, and they put all of the values that were male here. They might use something like this to kind of show you that in general or on average, a male will weigh more than a female, you know, of equal age or whatever they're trying to work with. So they just wanted to emphasize this versus this, and you can get a better feel for that than if you just have this, because you're not sure where the males or the females are. And in this case, you can obviously tell that females have a lighter weight in comparison to males based on the back-to-back stem plot. So you can use it in either way. Scatter plot. Let's go to scatter plot. Scatter plot is something we're going to talk about much more in depth in chapter 9 and I think actually in chapter 10. So that is something we'll work with in chapter 10. For now, we're just going to kind of show that a scatter plot can be used to represent data, and then from there we can try to find a relationship, whether it's linear or quadratic in nature. So this problem says Leonardo da Vinci used measurements of bones and body parts to predict height and body type of a person. He presented his findings in his famous drawing, The Proportions of the Human Figure, in 1492. Below is the graph of a sample of 55 adults, male and female. Each point on the scatter plot represents an individual's measure on both variables, his or her height and left arm length. So what they did is they measured your left arm, and then they wrote out your height. And they tried to see if there was a relationship between your left arm length and your height. So then they could measure somebody's, you know, bones, and they could, you know, if they found the remains of a person, they could measure their left arm, and then based on their left arm length, they could say how tall they probably were based on these findings. So this is something that statisticians do a lot, is they take data and they try to see if there's a relationship. For us, we could try, later on, we're going to talk about something called the line of best fit. So we might be able to average these values out and get this line right through the middle. And then that line we would use to predict value. So we're going to talk about this much more in depth in chapter 10. So for now, just kind of know what a scatter plot is. It's just a collection of data values that you plot them all on a graph. And then the goal normally is to try to see if there is a relationship, linear relationship, hopefully. And in other cases, you might be looking for exponential or quadratic in nature, but that'll be in a different class, not ours. Time series graph, I don't spend too much time on. Graphs of categorical variables. The distribution of category variables lists the categories and gives frequency of relative frequency and individuals who fall in each category. A pie chart, a circle represents the entire data set with the sections representing category percentages. So that's what pie charts are really good for, is showing percentages. A bar chart categorizes on the horizontal, categories are on the horizontal axis, x-axis, and the count or the frequency or percent is on the vertical y-axis. Bars do not touch in a bar chart, so it's not like a histogram. It has a very similar feel to a histogram, but it is a bar chart. Those you guys can kind of read over. I think you're kind of familiar with these two. I don't want to spend too much time on this. You guys can kind of look at that and figure it out for yourself. For this one, it says bursts are not, as you might think, of evenly distributed across all days of the week. Here are the average number of babies born on each day of the week in 2003. Make a bar chart for the data. So what we're going to do is, this isn't my favorite one to do. I feel like we use histograms much more, but bar charts can be good for what they're for. I'm going to do this in terms of thousands. So this will be 15,000, 10,000, and 5,000. And I had to do that because look at the values there. The bursts are 7,000, 11,000. So this is in thousands. Okay. And then down here, we're going to have, you know, let's go Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Let's go Sat. Okay, so this is days of the week. Okay, and then what I'm going to do is I'm just going to draw bars to represent, you know, our estimate for the values. So on Sunday there were 7,500 bursts. So here'd be about 7.5. So I'm going to draw a bar right here. Okay, and then on Mondays there were 11,700. So that would be a little bit, almost 12. Okay, and then Tuesday there were 13,000, so that's going to be a little bit above this. And then on Wednesday there were 12,500, almost 12,600. So that'll be a little bit below or a little bit above the 11,700. So maybe right about here. Okay, and then Thursday there were 12,500, so very similar, almost impossible to distinguish from this graph which one was more. This one actually should just be a hair shorter. And then Friday 12,400, so even slightly less. And then Saturday 8,600, so way less. And that would be our bar chart. Sometimes you'll see them shade every other one in for no reason. It's just to separate. But so why do you think there are fewer bursts on weekends? Okay, geez, I don't know. Bursts are not, as you might think, evenly distributed across all days of the week. Here are the number of babies. So it looks like Monday, Tuesday, Wednesday, Thursday, Friday, most of the bursts happen. And then Saturday and Sunday kind of have the lowest numbers. And this is a lot. I mean, this is a large sample, right? So why do we think that is? Well, who's doing the bursts? Doctors. So what if doctors are wanting to have weekends off? So one explanation may be, we may, or one answer, one possible reason could be doctors do not schedule C-sections or induced labor on weekends. That could be a reason. Now, again, there might be other things, but that makes sense to me. A doctor wants to have the weekend off. So if you're going to schedule a C-section, if it's not obviously not emergencies, you're still going to do it when you need to do it. But if you're going to induce labor or schedule a C-section, then you will pick a weekday when you're working. That could be one possible solution. There may be others, but that's just one that I can think of off the top of my head. Okay, so we're almost done. I believe this is the last page. Yep. So this is the last little thing. It says graphs of with a non-zero axis exaggerate the difference of categories, intervals represented by the bars. So one thing that this actually advertisers use, this is actually a technique they use to convince you, is they don't put a 0 on the axis. So it says highway fuel consumption with a vertical scale not starting at 0. So this is basically fuel economy. So they're showing you that in this case, the Honda Civic, so if we zoom in a little bit, the Honda Civic gets 36 miles per gallon, the Chevy Aveo gets about 34, and the Toyota Camry gets 31. But if you look at the graphs like they're written, doesn't it almost look like Honda gas mileage is like 4 or 5 times better then so the Civic's gas mileage is 4 to 5 times better than the Toyota Camry. That's the way the graph is trying to deceive you. Look at the comparison, this compared to that. The graph is trying to show you, oh my gosh, look how much better Honda Civic is. Now, if they did it correctly and they put a 0 here, now look, now it still shows that Honda is better than Camry. The Civic is better than the Camry in terms of fuel consumption. However, it doesn't look as exaggerated. So now this is a more realistic graph. This is somebody that's trying to be fair and show the data correctly. This is somebody that's trying to convince you to buy a Honda by making you look at the exaggerated fuel consumption or economy of the Civic versus the Toyota Camry. This is someone that's trying to give you all the data and show you, yes, Honda is better for the Civic and then the Camry in terms of fuel economy. However, it's not grossly exaggerated like in this. So this would be a bad graph, but that's actually the one people use to advertise. And it's not actually a lie, right? They're not actually lying to you. They're just trying to mislead you. Notice they're still saying 30. They're still showing you that Toyota gets 31 and Honda gets 36. So this graph is not actually a lie. It's not illegal to do, but it is trying to play on the fact that you don't understand how bar graphs work. This person is this is probably done by a person that has some background in statistics, or somebody that's trying to cover all their bases and fairly show each category. Maybe somebody that doesn't own a Civic or any of these brands. Some of these is just trying to be fair across the board. So this would be a better bar graph and more believable and more trustworthy. This one is still true, but this one is trying to mislead you, okay? Pictographs exaggerate the difference of categories in it by using objects or area or volume for data that is actually one-dimensional. So the number of passengers is a countable number, but they're trying to show you, look how much bigger it is, how much exaggerated it is by just showing you pictures. We're not going to do pictographs too often in this class. This is a more realistic graph that you would use, okay? So that's it for this video. I don't want to go too much into some of this stuff. I would say the misleading one with the not starting at 0 is the big deal. Pictographs and other things like that, I think you can kind of pick up on your own. But that's going to do it for the chapter 2 video. So this will be the last video for chapter 2. Thanks for watching.